As you can see from the title of this lesson, this tutorial is about orbital notation. Orbital notation is one of the three different ways that we can try to give a location or address to electrons as they're moving around the nucleus of an atom. The other day we talked about electron configurations and the diagonal rule and off-ball principle, which generated this little device that we use to give our electron configurations. Why do we have multiple notations? Well, the reason we have orbital notation is because it gives a more specific picture of the atom. The electron configuration could only tell us about the energy level and the orbital, the 1s. It didn't get more specific than that. Which orientation and which direction are they spinning? So the orbital notation is a much more specific picture of what's going on. The third notation that we'll learn, which is called dot notation, focuses in on a particular set of electrons, valence electrons, that are particularly useful when we are trying to explain how things react, reactivity of things. Just like electron configurations had a couple rules and principles that govern them, as do orbital notation. The two that apply to orbital notation are called the Pauli exclusion principle and something that we refer to as Hund's rule. The Pauli exclusion principle says no two electrons of the same atom are allowed to have the same set of quantum numbers. We learned that each electron has four different types of quantum numbers. The energy level, which we refer to as N, the orbital, SPDF, which is referred to as the L quantum number, the orientation, the direction that that orbital points, which is called the M sub L quantum number, and then lastly the spin quantum number, M sub S, which says whether the electron spins clockwise or counterclockwise. What the Pauli exclusion principle says is that no two electrons can be in the same place at the same time, because if two electrons were sharing the same four quantum numbers, that is exactly what that would mean. And two pieces of matter cannot occupy the same place at the same time. The second rule is called Hund's rule. It says orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second. Furthermore, all electrons in singly occupied orbital must have the same spin. When we were in class and we were discussing orientations, I showed you a lot of three-dimensional pictures, but a very simple way to show you what's going on is if we look at a p orbital. It is shaped like a dumbbell. So imagine I would be doing curls with this right here. That one orientation has two lobes. A lobe on this side, a lobe on this side. That's why it's shaped like a dumbbell. If we face it in this direction, we refer to it as the px orientation because it looks a lot like the x-axis. If that orbital's orientation were changed to look like this, and it were to face up and down, it's referred to as the py orientation. Looks like the y-axis. Last but not least, if we face it out at you, pointing toward you and pointing away from you, they refer to it as the pz. So a p orbital actually has three different orientations. So we want to know, are the electrons that are in there in the z, the y, or the x orientation of the orbital, not just the simply 2p orbital. Hund's rule says this: I have to put one electron into each of these orientations before I can put two in any of them. So I can't put the first two electrons in the z. One goes in the py, px, pz. Okay? One in each. Furthermore, they have to spin in the same direction. They'll all spin clockwise or counterclockwise until they get picked. You'll see how this works as we go through and start to do some orbital notation. So, just like we needed before, we're going to continue to use our energy off-ball principle because we want to make sure electrons are getting into the proper location. And let's take a look at some orbital notation of some different elements. Start with calcium. Calcium has 20 electrons. If I very quickly wrote up its electron configuration, it would look like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That tells us there's 2 electrons in the s orbital, 2 in this, or 6 in this 2p, but it doesn't distinguish between the 6 that are in the 2p. Orbital notation does, and this is how it does it. It breaks each orbital up into its orientations. So if I'm going to do orbital notation, it starts with a 1s orbital. You put the number of lines above that orbital as there are orientations. A sphere only has one orientation. Just like we did in class, no matter how I face this tennis ball, if there were no writing on it, you would not be able to tell the difference if it were this or this, right? Because there's just one orientation. The 1s gets one orientation. The 2s is still a sphere, one orientation. The 2p, like we just showed, has 3 orientations. So there's 1, 2, 3 that are all the 2p. A 3s is an s, it just has one orientation. A 3p is a p orbital, which means it has 3. And then lastly, the 4s is an s orbital, it just has 1. So in terms of writing lines above the orbitals, well, how many ever orientations they have is the number of lines it gets. An s has 1, so it was 1 line, 1 line, 1 line, 1 line. A p has 3, so each time I write a p, it has to be 3 lines. If I were to write a d, right, a d has 5 orientations, it would get 5 lines. And an f has 7, it would get 7 lines. Now, how do we fill these orientations? Well, what we do is we use arrows to represent the electrons. And the arrow, right, will tell the difference between these 2 electrons. So, according to what we would do, right, the 1s is going to have 2 electrons. So we draw one arrow going up. Going up indicates it spins clockwise. Then we come back and we draw one going down. If you notice, now I have all 4 quantum numbers addressed. The 1 is the principal. The s is the orbital. The line is the orientation. And the arrow is the spin. Right? And each of these gets a letter, right? Principal is N, orbital is L, orientation is M sub L, and spin M sub S. Now we'll just do the pictures with the arrows, but I want you to see how that works and why this is said to be more specific. The 2s has 2 electrons in it. They can't spin the same way, so one up, one down. The 2p gets 6, so we have to put 6 arrows in here. This is where which is off the screen now, Hund's rule comes into effect. It says I have to put 1 electron into each of these, and they have to spin the way, that's why up, 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 all being the same, before I can go back and pair any of these. So you have to go up, 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 then back, down, down, down. Back to the 3s, it gets 2, so you get an up arrow and a down arrow. The 3p gets 6, so we will go up, 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 down, down, down. And lastly, the 4s gets 2, it gets an up and a down. So as you can see, it's a little longer, but it draws something for every single electron that is in an atom, trying to give you the best representation that it can. Let's take a look at another one. let's look at something like iron. Iron symbol is Fe. It has 26 electrons. I always find it easiest to write the electron configuration first because then it helps you to know how many lines we need to draw. So, if we were to do the electron config for iron, we would fill the 1s first. It can hold 2. Then the 2s, it can hold 2. The 2p can hold 6. 3s, 2, 3p, 6, 4s, 2. We're at 2, 4, 6, 10, 12, 18, 20. We need 6 more. So this will just be 3d6. Right? It only needs 6 of the 10 that it's capable of. So when I go to draw my orbital notation for this, every time I see an S, I have to put 1 line. Every time I see a P, it's 3. Every time I see a D, it's 5. So if I go to fill this out, I'll have a 1s, it has 2 electrons, it's an up and a down. 2s, it's an S, so just 1 line, 2 electrons, up and a down. 2p is a P, so 1, 2, 3 lines, all 2p, and then we need 6, so up, 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 down, down, down. Next is a 3s, S only gets 1, up and a down. 3p, it's a P, so 1, 2, 3, all 3p, up, 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 down, down, down. Next is an S, 4s, it gets an up and a down. And then lastly, the 3d, it's a D, so it gets 5 orientations. 1, 2, 3, 4, 5, all called the 3D. Here is where it becomes very important to follow Aufbau principle coupled with Hund's rule, because I have to put 6 electrons in here. One of the 2 ways I can do that is by doing it correctly. Hund's rule says I put 1 in each of these, up, 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 all spinning the same way, before I compare it, and then my 6th one goes here. This is known to be correct. Here is how. A lot of you may say, well, why don't I just do a 3D that has 5, where I just go up, down, up, down, up, down. There's my 6 in the 3D. This is not correct for the following reason. One of the characteristics that the spin of electrons will provide is magnetism. Whenever we have unpaired electrons, ups without downs, that leads to substances being magnetic. Right? And they can display something they call paramagnetism. Whenever we have substances that are completely filled, ups with downs, no solos, like this would be, up, 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 down, 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 all counteracted, these things are not magnetic. They know iron to be deflected by a magnetic field, which proves that the Hund rule is in effect. If there were no unpaired ups, it would not be magnetic. That is why we have to put 1 in each before we compare any. Another common question that comes up is it okay to have lines that don't have anything in them? And the answer to that is yes. So let's look at an example where something along those lines happens. Let's take a look at something like aluminum. Aluminum gets 13 electrons. So if I start with its electron config, it would be 1s2, 2s2, 2p6 is 10, 3s2 is 12, 3p, just 1, even though a p can hold 6, gets us to 13. Now, if we do our orbital notation, I have a 1s, one line because one orientation, 2 electrons, and up and a down. 2s, one line, and up and a down. 2p, it's a p, so 1, 2, 3 lines, all 2p, 6 electrons, up, 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 down, down, down. A 3s is an s, so it just gets one orientation, up and a down. And now we get a 3p, and it's a p, so we have 3 lines that are 3p, and there's 1 electron. So you cannot create parts of orbitals. If I create a 3p orbital, I create all 3 orientations, the x, the y, and the z. Even if 2 of them are empty, you still have to draw them because a p orbital has 3 orientations. Now, you won't have to get as specific as to saying x, y, and z. We don't care about that, but you do have to draw that there are 3 orientations. So aluminum's electron configuration would look like that. One last one that we want to show you, right, would be copper. And I want to show you copper because copper is an exception. Right? There are many exceptions, and I will highlight them in class, but I wanted you to have an exception for review, right, to kind of show you why the exceptions tend to be. If I'm going to draw copper, copper has 29 electrons. If I start with an electron config, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9 is what we would think copper is. It is in fact not 3d9. Right? And here is why. If I draw orbital notation for this, I see an s, so there's 1, it gets an up and a down. I see an s, it's a 1, it's an up and a down. I see a p, p's get 3, up, 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 down, down, down. I see an s, just gets 1, up and a down. Again, a p, it gets 3, up, 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 down, down, down. 4s has 1 and a d has 5. And I'm going to show you why this exception occurs. This is not the real ending of copper's electron config. If we were to draw it, it would look like this. Right? We would go up and a down in the 4s, and then up, 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 down, 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 down in the 3d. That leads to there being a partially filled orientation of the 3d. A d orbital is much, much, much more energetic than an s. Atoms like to be as stable as possible. So a full d orbital is actually more stable, okay, than a 4s orbital. So because an s orbital is small, if it's unstable, its energy can only reach a certain point because the s orbital is small. A d orbital is much, much larger, has more energy, so if it is unstable, right, it is not energetically favorable. So what the atom does is it takes an electron out of the 4s and it completes that 3d orbital. So now we have an entirely filled third energy level, which gains stability. We fill a higher energy orbital, which gains stability. And then we have an unstable small orbital in a higher level. And that is what atoms do to gain stability. There are very few examples. We'll probably only focus on 3 or 4 of the exceptions. I don't want to overwhelm you, but I wanted you to see one and understand why it occurs. So the actual ending for this config is actually 4s1, 3d10. And if you check in the back of your book, that will match what you're seeing for copper, among other things. And you'll notice that that pattern follows. Right? That elements that are in the same group as copper tend to take an electron from their higher s orbital and put it into that d orbital to stabilize it. So these are electron notations, right, based off electron configs and the diagonal rule. If you're having any confusion about it, please stop in for some help. Otherwise, I hope this cleared up any confusion that you may have had.